Hello everyone, I'm Laixi Shi. I will introduce a work of fusion-based digital image correlation framework for stream measurement. Here are my co-authors. Stream measurement is an essential task in various real-world applications. For example, for damage detection. 1 month ago, we installed a new machine component. Now we want to detect whether there is some damage in this component. So the strain difference between the reference surface and deformed surface can determine whether there's damage. But how can we measure the strain on the surface? There are mainly two kinds of non-contact optical technologies. One is interferometric. However, the experimental equipment and conditions are hard to satisfy in many scenarios. So we choose another kind of non-interferometric. Among them, which is a widely used digital image correlation one. By comparing the reference surface and deformed surface, we can use the IC to get stream measurement. If there's no damage, then the stream measurement will be uniform. If there's some damaged part, the stream measurement will have some big deviation like the yellow region. Our target scenarios are for a curved surface of a large three-dimensional object. To use the IC, there are mainly three challenges. First, we are targeting a curved surface, which cannot be handled by the classical 2D DIC, which is limited to planar surface. Second, the existing 3D DIC module usually need inapplicable experiment setup and multiple cameras or marker on surface. Third, as the target object is very large, comparing to the distance between the camera and surface, a single image usually cannot capture a full field and high resolution image of the surface. To address these challenges, our framework chooses to unfold the curved 3D surface to 2D, and also we only need very simple experimental setup, one single camera, and need no operation on the 3D surface. Most importantly, we incorporate image fusion principle into the framework to deal with the large size of the object, stitching multiple images to a very big one. Here is our framework pipeline, which consists of 3 modules. The first image deblur module will deblur these blurry observations from the camera. Then we're stitching them into 2 very big final super resolution to the image for the DIC module to get the stream measurement map. So in this presentation, we will first introduce the process of the image simulation. Targeting a cylinder surface in this work, we will have a sequence of images by moving the camera around the surface. And such as the blue, yellow, and yellow-red region, they will be covered by different images in the sequence. The camera pulls an unknown for each image, since they will have some unknown random perturbation. We move camera along the XL direction to get 5 images, and then move forward along the tangential direction along the trajectory, and so on and so forth, and capture 160 images in total for one sequence. Then we will introduce our framework by introducing these 3 modules separately. For the first image deblur module, the goal is to simultaneously recover the image xi and the blur kernel k from the observation yi, from the observation of their convolution yi. This blind deconvolution problem usually imposes without any other assumptions. So as non-focused blur is usually considered as Gaussian or plane, we assume the kernel K is a truncated Gaussian with unknown standard deviation sigma. So the method have 2 steps. First, we will get the initialization kernel K0. by using Werner filter and minimizing the normalized sparsity loss in possible region. Then estimate the kernel K and Xi by minimizing this optimization problem with the total variation regularization. Here the result of image deblur module. In step 1, we can get initialization kernel, which is similar to the ground truth. Then in step 2, we can get a accurate deblurred image estimation XI hat. Then we will introduce the most essential module in this framework. First, we introduce the pinhole camera module. Here, the equation shows the process of point U in the 3D space project to the camera plane, point X, with the rotation R and translation vector T, which can represent the camera pose. So with camera pose, we can project the pixel X in the camera plane back to the 3D object reference if we know the 3D geometry. The goal of this module is to reconstruct the superlative 3D surface on the cylinder with the input of a sequence of images. Each of them cover narrow field of the surface. So module have 2 steps. First, we want to estimate all the unknown camera pose of these 160 images. Then, with all the camera pose, we can project all the pixel of images back to the 3D surface for image fusion, and then interpret it to get the final unfolded to the image for later DIC module. The most essential part is how to estimate all the camera poses. So the camera pose estimation for all the image in a sequence can be seen as multiple sub-problems. With the first image's camera pose as reference, by induction, we assume that we can know the camera pose of a reference image xj. Then, with the camera pose of this xj, we want to estimate the pose of one image xi in each subproblem. So, how to estimate the camera pose of image xi with the camera image pose of the reference image xj? First, we will find a set of matching feature points between these 2 images and form the set of feature points AJI. Then, as we already know the camera pose of the reference image xj, we will project the feature points from xj to the 3D object. Finally, we will have many 3D to 2D matching point pairs between the 3D surface and the target image xi. It leads to the ubiquitously perspective endpoint problem, which with the goal to estimate the camera pose of xi using the 3D to dimension points MJI. We propose a method called RRWLM to solve the PNP problem, which is to iteratively minimizing the robust reweighted nonlinear least square problems. Here, WM means reweighted. It is the inverse of the measurement error for the IM's feature, which softly rejects the bad feature points. We also propose a refined method RRWLM. In this method, the only difference between RRWLM and RRWLM is that We combine bundle adjustment principle into this method and use the feature point in all the images in this set. Li means the set of images that have overlapping with our target image xi. So we use all the feature points we use all the feature points between the image xi and the set Li instead of only one reference image xj. So we take advantage of more feature points. Here we show the image stitching experimental results. We're using two criteria to test the performance of our image stitching method with comparisons with 3 existing PNP state of Rs. So the two criteria is the average pulse error and the PSNR. From the result, we can see that we achieve much less average pulse error and higher PSNR. Here are the final image stitching results. A is the ground truth, B and C are the image stitching result by our method, and the best state of Rs PNP method. Through the final module, we can get the string measurements from the image stitching results of the image before and after deformation. This is the result using the stitching results of only 10 images to do image fusion. The string measurement results by our method and baseline are both okay, comparing to the ground truth. However, the cover region by 10 images is too small for later DSC. We need to stitch more images for full field of the large 3D surface. When using image stitching by all the 160 images, which is a very large field of the surface, the baseline is not applicable owing to accumulation of errors. Well, our method can achieve applicable results comparing to the ground truth. For conclusion, first we propose an end-to-end fusion-based DSC framework for 2D string measurement along curved surface of large 3D objects, which extends the application of 2D DSC to curved surface in large size. We also introduce a general pipeline for future works. Second, we incorporate image fusion principle into string measurement framework. The proposed method for the essential PNP problem achieves better performance with comparison to prior works and meet the stringent requirement for DSC-based string measurement. Thanks for listening. If you have any problem, we're happy to answer it. Please contact us.